All right, we're here for AP Physics vertical motion. Take a look at problem 3. It says person staying at the edge of the roof throws ball A vertically upward with initial velocity of plus v naught, throws a second ball B downward at negative v naught, same magnitude. Both balls fall to the ground past the edge of the building. Assuming no air resistance, what's the velocity of A as it passes the level from which it was thrown on the way down? So this is going to look like this. We say, okay, here's my building. This is problem 3. All right, dunk, jerk. Right. Right. We're going to go ahead and we're going to throw ball A, and it's going to go up at v naught, and ball B, we're going to throw from that same height, but ball B, we're going to throw down. Assume this is starting from the same spot, from the same height, but starting down here at negative v naught. Okay, so wonk, 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 equal and opposite magnitudes. And so the question is, first question is, ball A here, it's going to go up, it's going to come to a stop, it's going to come back down, right? When it gets back to this initial height, you say, how fast is it going to be going? We know it's going to get slower and slower. When it gets to the peak, the speed is 0. And on the way down, it's going to get faster and faster. And when it gets back to this height, well, it's just going to be identical here. It's going to be going at negative v naught. Okay, assuming no air resistance, we know that that is the case. Okay, how do we know that? Well, my favorite way of explaining this is with a VT graph. And we say that at the start, that ball has an initial velocity of positive v naught, but the graph for it looks like this. You remember that this line, the slope of a VT graph is the acceleration. So we know the slope of this is negative g, right? And it's a constant slope because it's a constant acceleration. And because of that, there's this huge amount of symmetry here. We know that, you say, what's that? That's the displacement up to the peak. And so if I do an equal area, right? Well, because it's the same rise to run ratio here, right? Okay, the triangle that will give you the equal area here, right? Might not have drawn that real perfect, but this area being equal and opposite, right? That'll be when I get back to the same height, right? And you say, well, gosh, same displacement, total displacement is 0, right? Positive, negative displacements adding to 0. And you say, well, gosh, for that to happen, because it's the same rise to run, they have to be symmetric triangles, right? Symmetric triangles. And that means the magnitude of this is the same as the magnitude of this. And that means over here, right? That this is negative v naught, okay, by symmetry. And so that is the deal. So we know that our answer for part A is that the v of ball A at the end there is just negative v naught, okay? Let's see. Then what? This takes us to, right? Assuming no air resistance, how will the velocities of the two balls on striking the ground compare to each other? And explain your reasoning. Before I dive into that, it is worth just a quick reminder. When we studied vertical motion in honors last year, a problem like this where you throw a ball straight up and it goes straight up and comes back down and returns to its initial height. Do you remember that there were like 5 special things that you were supposed to remember about a problem like that? Let me list those out here. Okay, what were those 5 special things that we knew about a problem like that we discovered? And you see, if I run through, 1, we remember that the acceleration is negative g. 2, we remember that the velocity at the peak is 0. Number 3, if it returns to the same height, then by definition, the total delta displacement is 0, okay? Or you could say that the delta x up is equal but opposite to the delta x on the way back down, right? If it returns back to where it came from, the total displacement's got to be 0. And then 4, we remember that the time to the peak is half of the total time for it to go up and down, okay? Or you could say that the time up is equal to the time down. Okay, if to come back down from that peak. And then lastly, and this is what has a bearing on this problem, is that at any given height, right? At any height here, okay, on the way up, on the way down, right? Chook, chook, those velocities are equal and opposite, right? Okay, at any particular height that you want to look at, right? They balance out, okay, because of the symmetry here in the VT graph. And so we can say that at any particular height, the velocity on the way up is equal but opposite to the velocity on the way down. Okay, and these were like 5 special things that we knew about this type of problem where something is launched straight up in the air, goes straight up, comes back down, that we figured out from last year. And then what's special about this list? We're going to be able to use these same ideas in solving projectile problems. Because remember, the key thing about projectile problems is that they're really just 2 motions happening at once. One motion is this motion, this up and down sort of motion in the y-axis with that constant acceleration in negative g, and the other motion is just a constant velocity sideways. So you can put those together, you get that parabola out. So that's so these ideas are important, and these are things that you should honestly just recognize when you see a situation like this. Okay, moving onward. Let's get to part B. Part B says, assuming no air resistance, how will the velocities of the 2 balls on striking the ground compare with each other? Well, we're talking now about when they get to the ground. And you say, well, this ball starts off, the green one starts being thrown down at negative V naught, and gravity is going to accelerate it from there, right? And it's going to get faster and faster, right? And when it gets to the ground, it's going really fast. And you say, well, isn't it true that from here on out, this ball A had to get thrown up and go up and come back down, but once it's here, it's identical conditions to the green ball. It's the same location. It's going to have the same displacement, the same acceleration, the same initial velocity. That's 3 variables the same. And with kinematics, remember, once you have 3 variables, that locks the other 2. And so this motion is going to be identical, right, from here on down. Okay, so ball A, like from here on out, the motion's identical to ball B. So there you have it, right? Okay. So those velocities, when they hit, are going to be identical. Yep. V at the ground, let's see here. Let's say V of A at the ground is going to be equal to V of B at the ground. Okay, their motions are identical from there on out. Okay, part C. Part C says, visualize the same experiment with air resistance now. Now, how do the velocities compare? Will they be equal or unequal? If unequal, which one's bigger and why? And so the deal is, this one starts the V naught, A starts the V naught up, B starts the V naught down. But A, as we move up, now we have air resistance. We're slamming into air molecules. It's going to be slowing the ball down. Will it make it as high as it did the first time? See, no, it's not going to make it as high because it's getting slowed down by the air, right? So now, if you fell from this height, are you going to have that same speed when you get to there? You say, no, I'm not going to have the same sort of speed as if I fell from way up here. I'm only falling from here now because air resistance slowed me down. And so now I'm not going to get back up to V naught. Okay, my speed won't be V naught when I get here. It'll be slower. And so now from here on down, right, these motions were identical with no air resistance, but now the red one, ball A, is starting slower. And so it turns out that then the green ball, ball B, is going to be going faster when it gets down here with air resistance than ball A will, because A has been losing energy. That's another way of looking at energy, pushing against that air, doing work. That's going to be slowed down, losing more energy. So it starts off here with less energy than the green one does. Another way of thinking about it, it delivered some energy to the air, and it had a longer path. It was doing more workforce through more distance, using that energy idea. With kinematics, just recognizing it's not going to go as high, and so it's not falling from as high. It's not going to get to that same V naught. So there you go. So we would say that the velocity at A at the ground is going to be less than the velocity of B when it gets to the ground. Okay, why? And you can talk about the energy argument, or you can talk about the fact that essentially this is getting dropped from lower because it's not going to make it as high. And so it won't be up to speed v naught when it gets back to the level of the roof. Let's see, moving onward. Let's talk about part D. Okay. Is it okay that I don't write out that explanation I just verbally told you? Yeah, I thought you'd be okay with that. That's why you watch the video, right? Okay, part D. Suppose the third ball C, okay, we're gonna take a third ball, and this one we're gonna launch sideways from the edge of the rough. So like all these are supposed to be launched from the same spot. Unfortunately, I'm like running out of space here. So I'm just gonna draw it starting over here, okay? But this is like the edge of the roof. Here's ball C. This one we're gonna launch with the same vertical speed, but that's just a component of its total velocity. You say it's in fact going to have a horizontal component of the same magnitude. So in other words, same magnitude up, that magnitude horizontal too, it's going to be going at a 45-degree angle, like that. Okay? And this has okay, and this is a V naught, and this is a V naught. Okay? And so the question is, assuming no air resistance, how will the size of the total velocity of C when it hits the ground compared to the velocity of A when it hit the ground, the red guy, right? And no air resistance for this one. And you say, well, I know that when I launch this, it's a projectile. And we say the vertical motion is the same, right? There's only one force acting up and down on this ball, and that's gravity, the same as is acting on that. So the vertical part of this guy's motion will be identical to the red guy's motion. It just has this sideways motion also. Are there any forces pushing sideways on this ball? And the answer is no. So that horizontal motion is going to be constant. So when this thing does its motion, right? Okay, when it gets here, at the end, its vertical motion is identical to the red vertical motion because there's only one force on the y-axis, it's gravity, the same one for both. Same initial velocity, same displacement, same acceleration, right? Everything's same. So it's going to end up with the same identical final velocity as all these guys, right? But it also has this horizontal velocity. I probably should have made that a dotted line, huh? Yeah, probably. But it still maintains that initial horizontal velocity, right? So the total velocity for this guy is going to be, you know, like that. Wish I'd drawn that a little nicer. So this is its total. We can call that VC total, right? And so VC total is going to be equal to, and this is the same as VA final, right? The VA at the ground. So it's going to be like this total, this hypotenuse of a right triangle, right? Y and X make a right angle. This means I can use Pythagorean theorem. You say it's going to be the root of the final velocity of A, right? V of A at the ground squared plus V naught squared square root, right? You know what I mean? Okay, so that's going to be the velocity of it when it gets to the ground. And let's see here. So that's how it's going to compare the final velocity of A. It's just VA ground, right? And this is going to be the root of VA ground squared plus V naught squared. Okay, let's see here. What else we got? That's it. Okay, that's part D. Okay, that's the end of that problem. Problem 3. So a little bit of a reminder of those 5 critical things to know about this sort of special up and down motion with constant acceleration, negative g. And then reminding you of some of these bits of like how we deal with projectile, with splitting into components and using Pythagorean theorem. Good stuff.